A tiny pinpoint of light holds a secret older than our planet. That faint glow is the echo of a black hole from the dawn of time. We are about to journey to the edge of everything we know to uncover 50 astonishing facts about the universe's most distant black holes. By the end, you will understand how these dark giants shaped the cosmos and rewrote the rules of physics. How did they grow so massive so quickly, and what invisible forces guide their evolution? What single question about the early universe would you most want one of these ancient beings to answer? That faint glow is a message from the past, written in the language of light. To understand these black holes, we must first grasp what distance means in the cosmos. A light year is not just a measure of space, but of time. It is the staggering distance light travels in one entire year. When we observe a black hole 10 billion light-years away, we are not seeing it as it exists today. We are witnessing light that began its journey to us 10 billion years ago, a snapshot from when the universe was in its cosmic infancy. This is the concept of look-back time, a fundamental key to unlocking the past. The most distant objects are also the oldest, their light serving as cosmic time capsules. To measure these incredible distances, astronomers rely on a phenomenon called redshift. As the universe expands, it stretches the very fabric of space. Light waves traveling through this expanding space get stretched too, shifting toward the red end of the spectrum. Think of the sound of a siren on a passing car, how its pitch drops as it moves away. Redshift is the visual equivalent for light. The more stretched and reddened the light appears, the farther the object has been carried away by the expansion of the universe, and the farther back in time we are looking. This redshift is our most vital tool, a cosmic ruler that allows us to peer back to the era of the very first black holes. That reddened light carries a specific cosmic address, leading us to the current record holder. Its official designation is J0313-1806, a quasar powered by a supermassive black hole of almost incomprehensible age. The light we see from it began its journey over 13 billion years ago. We are witnessing this object as it existed a mere 670 million years after the Big Bang itself. To grasp that scale, if the entire history of the universe were compressed into a single year, this black hole was shining when the cosmos was just a few weeks old. The true shock, however, is not merely its age but its size. This black hole already weighed in at over 1 billion times the mass of our own sun. Finding a gravitational giant of that scale in the cosmic nursery is like walking into a kindergarten classroom and discovering a fully grown adult. It simply should not be there according to many of our conventional models. How did it gather so much material so quickly? This single object forces a profound question, challenging everything we thought we knew about how quickly black holes can form and grow. Its very existence suggests that the seeds of the first black holes must have been colossal from the start, or that they grew by some mechanism we have yet to fully understand, feasting on the primordial gas of the infant universe at a rate that defies our current physics. The billion solar mass giant we just encountered is not the only kind of black hole in the cosmos. In fact, the universe creates them in different weight classes, each with a unique origin story. The most common type is the stellar mass black hole. These form when a massive star, many times larger than our sun, runs out of fuel and collapses under its own gravity in a cataclysmic supernova explosion. The resulting black hole is typically a few dozen times the mass of the sun, a dense remnant of a single star's death. They are the universe's default setting for black holes scattered throughout galaxies like ours. But then there are the supermassive black holes, the true titans that rule the centers of nearly every large galaxy. These are the ones we find at the edge of the observable universe. They are not merely large, they are of an entirely different order of magnitude, weighing in at millions or even billions of solar masses. So why is it that we only see these supermassive behemoths from the cosmic dawn? The answer lies in visibility. A lone stellar mass black hole is incredibly dark and nearly impossible to spot from billions of light years away. A supermassive black hole, however, often announces its presence with a cosmic roar. As vast amounts of gas, dust, and even entire stars spiral into its gravitational grip, this material doesn't fall in silently. It forms a searingly hot, spinning disk of matter called an accretion disk, which glows with the intensity of trillions of stars before it crosses the event horizon. This process turns the black hole's immediate environment into the brightest persistent object in the universe, a quasar. It is this phenomenal, galaxy outshining brilliance that allows us to detect them from the deepest reaches of space and time. Without that ferocious appetite lighting the way, the distant cosmic darkness would remain impenetrable. That ferocious appetite lighting the way has a name, the quasar. Think of a black hole not as a simple vacuum cleaner in space, but as the engine of the most powerful lighthouse in the cosmos. When a supermassive black hole actively feeds, the material destined to fall in does not plunge straight down. Instead, it forms a vast, swirling vortex of gas and dust called an accretion disk. This disk spins at nearly the speed of light, and the friction within this chaotic maelstrom is so intense that it heats the material to millions of degrees. The result is a blaze of radiation so powerful that a single quasar can outshine every single star in its home galaxy combined. It becomes a cosmic beacon visible clear across the universe, a piercing needle of light in the cosmic haystack. This is why quasars are our primary tool for finding the most ancient black holes. We are not looking for the black hole itself, an object from which no light can escape. We are looking for the brilliant, frantic glow of its final meal, the last scream of matter as it crosses the point of no return. Without these dazzling beacons, the early universe would be a dark and silent place to our telescopes. They act as guideposts, illuminating the most distant and dramatic chapters of cosmic history. But how do you observe an object that, by its very nature, swallows light? Astronomers are cosmic detectives, solving this ultimate locked room mystery by looking at everything the black hole touches. One of the most reliable methods is to watch the dance of stars near the galactic center. By tracking the orbits of these stars over many years, scientists can measure their incredible speeds. If a star is whipping around an apparently empty point in space at thousands of kilometers per second, it tells us one thing: something with immense gravity is hiding there, pulling the strings. The faster the star moves, the more massive the unseen object must be. It is like deducing the presence and weight of a person you cannot see by watching how a dog strains at its leash. Another method focuses on the black hole's brilliant accretion disk. By analyzing the specific colors and energies of the light streaming from this hot plasma, scientists can determine the disk's temperature, its composition, and even how fast it is spinning. This light carries a fingerprint, a detailed report on the extreme physics happening just outside the event horizon. Finally, there is a phenomenon called gravitational lensing. A black hole's gravity is so powerful it warps the very space around it, acting like a cosmic magnifying glass. When light from a more distant galaxy passes near this warped space, its path is bent, often creating multiple, distorted images of that background galaxy or stretching it into a bright arc. This effect, predicted by Einstein, allows astronomers to literally see the shadow of the black hole's gravity painted across the sky, mapping its presence by how it twists the light of everything behind it. We see the unseeable not by looking at the void itself, but by reading the profound story written in the things that orbit it, feed it, and bend around its dark heart. Peering through the cosmic fog requires a special kind of eye, one that sees not invisible light, but in the high-energy realm of X-rays. This is the vital role played by the Chandra X-ray Observatory, a space telescope that has fundamentally changed our search for the universe's darkest secrets. While optical telescopes show us the brilliant glow of quasars, that visible light can be blocked or dimmed by vast clouds of interstellar dust. But the physics of a feeding black hole provides another signal, one far more penetrating. As gas is violently accelerated and heated to millions of degrees in the accretion disk, it doesn't just glow with visible light, it screams with high-energy X-ray radiation. These X-rays are so powerful they can punch straight through the cosmic dust that obscures our optical view, traveling billions of light years unimpeded. Chandra, orbiting high above Earth's X-ray blocking atmosphere, is our perfect sentinel for this invisible light. It captures these energetic screams, translating them into data that reveals black holes which would otherwise be completely hidden from our sight. It is like listening for a whisper in a storm, using a specialized microphone that filters out all the noise. Chandra's deep, long stares into the darkness have uncovered countless supermassive black holes in the early universe, not by their visible fire, but by the pure, high-energy signature of their final, frantic feast. This X-ray vision confirms that the cosmic dawn was filled with far more of these gravitational giants than the visible quasars alone could ever tell us. While Chandra listens for the X-ray screams of these ancient giants, a new observatory is painting an even deeper portrait of the early cosmos. The James Webb Space Telescope sees the universe in a language of light our eyes cannot perceive, infrared. This is the crucial key to the deepest past. As the universe expands, the light from the most distant objects is stretched to extraordinary degrees. What began as visible light or even ultraviolet radiation is redshifted far into the infrared part of the spectrum. For telescopes like Hubble, this light becomes invisible, a faded signal lost to the cosmos. But James Webb is specifically designed to see this infrared glow. Its giant golden mirror acts as a colossal light bucket, gathering these faint, stretched whispers from the edge of time. It is not just a more powerful telescope, it is a time machine tuned to the specific frequency of the cosmic dawn. With it, astronomers are not just finding more of these distant black holes, they are seeing the galaxies they live in. For the first time, we can observe the intricate dance between a newborn supermassive black hole and its host galaxy, watching how they feed each other and grow together in the universe's first chapters. James Webb is pushing the frontier back to a mere 200 million years after the Big Bang, into an era we once thought was forever beyond our sight, revealing a universe that was already bustling with unexpected activity far sooner than anyone predicted. This rapid growth presents one of the most baffling puzzles in modern cosmology. How could a black hole possibly gain 1 billion solar masses in less than 1 billion years? The standard model of stellar collapse simply cannot explain it. If the first black holes were born from the deaths of the very first massive stars, they would have started out as relatively small seeds, perhaps only a few dozen times the mass of our Sun. For one of these to grow into 1 billion solar mass giant, it would need to feast on surrounding gas at its theoretical maximum rate, and do so continuously for its entire existence. It is like trying to grow an oak tree from an acorn in a single season, demanding a perfect, uninterrupted supply of water and sunlight with no delays. The early universe was likely too chaotic for such a perfect and sustained feeding frenzy. This glaring discrepancy has forced scientists to propose far more exotic and dramatic birth scenarios for these cosmic giants. One compelling theory is known as direct collapse. Imagine a pristine cloud of primordial gas in the early universe, a cloud so immense and dense that it bypasses the entire process of star formation. Instead of fragmenting into thousands of individual stars, this entire colossal cloud, weighing many thousands of solar masses, simply collapses in on itself all at once. There is no supernova, no stellar fireworks, just a silent, catastrophic gravitational failure. The result would be the instantaneous creation of a supermassive black hole seed, a behemoth born not from a single dead star, but from a whole stellar nursery in one go. This provides a massive head start, a seed already weighing tens of thousands of solar masses, giving it a huge gravitational advantage to begin its cosmic feast much sooner. Another possibility involves a frantic, chaotic environment where early black hole seeds merge together repeatedly. In the crowded core of a nascent galaxy, these dark objects could have been drawn together, colliding and combining their masses in a series of violent unions. It is a gravitational pyramid scheme, building mass through relentless consolidation. Yet, even this process may not be fast enough on its own to explain the most extreme examples we observe. Perhaps the true answer lies in a combination of these factors, a perfect storm of conditions where massive seeds formed via direct collapse, then gorged themselves on the dense, plentiful gas of the infant universe, all while frequently merging with their neighbors. This triple threat of growth mechanisms could have propelled them to unimaginable sizes at a speed that still challenges our understanding of physics, suggesting the universe's infancy was a far more violent and efficient forge for these dark giants than we ever dreamed. These cosmic engines do not just live within their galaxies, they command them. The relationship between a supermassive black hole and its stellar home is a violent, intricate dance of creation and destruction. When a black hole feasts, the energy it releases does not simply vanish into the void. It erupts outward in two colossal ways. First, the intense radiation from the blazing accretion disk floods the galaxy with so much energy that it heats up the vast reservoirs of cold gas, the very raw material needed to form new stars. This is like turning up the heat in a freezer, preventing the water vapor from ever condensing into snowflakes. The gas becomes too hot and turbulent to collapse under its own gravity, effectively putting a halt to star formation in a process called quenching. But the black hole's influence is even more direct. Often, along the black hole's spin axis, focused beams of charged particles are launched at nearly the speed of light, carving through interstellar space for thousands of light years. These relativistic jets inject enormous energy into the galaxy's heart, violently stirring the gas and blowing it clear out into intergalactic space. This incredible process, known as feedback, means the black hole ultimately regulates the galaxy's growth. It is a cosmic self-regulation system. The galaxy feeds the black hole, and in return, the black hole's furious activity determines how many new stars the galaxy can build, shaping its size, structure, and ultimate fate. A too active black hole can essentially starve its own galaxy, leading to a quiet, aging giant filled with old stars and little new life. Before those billion solar mass giants could dominate, the very first seeds had to be planted in the cosmic dark. These were the primordial black holes, born from the cataclysmic deaths of the universe's first generation of stars. We call these stellar pioneers' population 3 stars, and they were unlike anything that exists today. Forged from the pristine hydrogen and helium left by the Big Bang, with no heavier elements to cool them, these stars could grow to staggering sizes, perhaps hundreds of times more massive than our Sun. Their lives were brilliant and short, burning through their nuclear fuel in only a few million years before collapsing in titanic explosions. From their ashes, the very first stellar mass black holes were born. Spotting one of these original seeds, however, is a challenge of cosmic proportions. They are ancient, dark, and relatively small, having not yet begun the ferocious feeding that would turn them into quasars. They drift through the silent expanses of intergalactic space, invisible against the blackness. Their faint gravitational whispers are drowned out by the roar of their supermassive descendants. Finding one would be like discovering the fossilized footprint of the very first creature to walk on land, a direct window into the processes that built the cosmos. It would confirm our theories about the universe's first light and reveal the initial conditions for all the black holes that followed. This search is one of astronomy's ultimate quests, a hunt for ghosts that could finally illuminate the true dawn of our structured universe. The violent mergers that built those first supermassive black holes sent tremors through the very fabric of reality. These tremors are gravitational waves, ripples in space-time predicted by Einstein over a century ago. When two massive black holes spiral towards each other in a final, deadly dance, their immense gravity churns the cosmos around them. They do not merge quietly. They send out waves of gravitational energy that travel outward at the speed of light, stretching and compressing everything in their path. For decades, these waves were just a theory. Then, in 2015, the LIGO Observatory made the first historic detection, feeling the space-time shudder from two stellar mass black holes colliding over 1 billion light-years away. It was like hearing the universe for the very first time. Today, a global network including LIGO and its European counterpart, Virgo, routinely listens to these cosmic ripples. But the ultimate goal is to tune into the deepest past. The mergers of the very first supermassive black hole seeds would have been the most powerful event since the Big Bang itself. Their gravitational wave signal would be a low, rumbling hum that has been traveling for over 13 billion years. Our current detectors are not quite sensitive to this primordial background rumble, but a new generation of observatories planned for space, like the Laser Interferometer Space Antenna, or LISA, are being designed specifically to listen for it. This would open a window to the cosmic dawn that is completely separate from light, revealing the hidden construction work of the universe as the first dark giants were forged in collision after collision. It is the sound of creation itself, a silent symphony from the beginning of time. Yet the nature of these first seeds remains one of cosmology's great debates. There are two leading candidates for what planted the initial darkness, and they are on opposite ends of the cosmic scale. The first theory points to the remains of those earliest colossal stars. When a population 3 star hundreds of times the Sun's mass ended its short life, its core would have collapsed into a black hole. But even from such a giant star, the resulting seed would be relatively modest, perhaps only a few hundred solar masses at most. While that is enormous by our standards, it is a tiny pebble compared to the billion solar mass mountain it needs to become. Growing from this small seed requires a long, perfect, and uninterrupted feast, a scenario that seems increasingly unlikely in the turbulent early cosmos. The second candidate offers a far more dramatic beginning, the direct collapse black hole. Picture a vast, pristine cloud of hydrogen gas in the early universe. Before it can fragment to form a cluster of stars, the entire cloud, weighing 100,000 suns or more, collapses directly under its own weight. There is no star formation, no supernova, just a silent, catastrophic gravitational failure that births a massive black hole seed in one single, swift event. This is not a pebble, but a boulder, a huge head start that can grow into a supermassive giant much more easily. The question is, which path did the universe prefer? Did it build its giants patiently from many small seeds, or did it forge them instantly from colossal clouds? The answer likely lies in a messy combination, a cosmic tug of war where both processes occurred in different environments, setting the stage for the dark giants we observe at the edge of time. A black hole without a home is one of the universe's most ghostly concepts. These are the theoretical wanderers, supermassive black holes flung from their galactic cores into the endless dark. Such an event requires a cataclysm of almost unimaginable scale, typically the collision of two galaxies. When their central black holes spiral toward each other, their immense gravitational dance can act like a cosmic slingshot. If a third black hole is involved from a previous merger, the complex interplay of forces can eject one of the titans entirely, hurling it into intergalactic space at speeds of millions of miles per hour. This creates a naked black hole, stripped of its stellar city and drifting alone. Spotting one of these isolated giants from the distant, early universe is a monumental task. Without a host galaxy to provide gas for a brilliant accretion disk, and with no surrounding stars to give away its position through their motion, it becomes a nearly invisible phantom. Yet there is a potential clue. If such a wanderer were to pass through a dense cloud of primordial gas, it could briefly flare into visibility, a single, unexplained point of X-ray light with no galaxy attached. Finding one would be a direct confirmation of the violent, chaotic mergers that built the cosmos, revealing that the process of galaxy assembly was a messy, explosive affair where even the mightiest gravitational anchors could be torn from their moorings and cast adrift. These dark giants are not the only invisible architects of the cosmos. Another, far more mysterious force was also at work in the early universe, a ghostly presence we call dark matter. This unseen substance, which makes up over 80% of all matter, does not emit or absorb light, revealing itself only through its gravitational pull on galaxies. For decades, its true nature has been one of physics' greatest enigmas. But what if the solution to this mystery is hidden in the same cosmic dawn we have been exploring? A fascinating theory suggests that some, or even all, of this dark matter could be composed of a vast, unseen population of primordial black holes. These would not be the supermassive giants, but trillions upon trillions of smaller black holes, each perhaps no more massive than an asteroid, forged in the chaotic first second after the Big Bang. In that initial furnace of extreme density, random fluctuations could have caused pockets of space to collapse directly into black holes of almost any size. If this happened on a small scale, the universe could be filled with these ancient microscopic gravitational pits, drifting through the darkness like a fine cosmic mist. They would be the perfect candidate for dark matter, invisible yet possessing the exact gravitational influence we observe. How could we possibly test such an idea? The answer lies in a cosmic phenomenon we have already discussed: gravitational lensing. If a vast swarm of these small black holes exists, one of them would occasionally drift in front of a distant star. Its gravity would act as a tiny lens, bending the star's light and causing it to momentarily brighten before fading back to normal. Astronomers have searched for these brief flashes, and while some candidate events have been seen, there are not nearly enough to account for all the dark matter. This suggests that if primordial black holes are a part of the dark matter puzzle, they are likely only a small fraction. The search continues, a cosmic hunt for the universe's most pervasive ghost, which may yet be composed of its very first darkness. The very existence of these ancient giants challenges the bedrock of modern physics. They are not just cosmic oddities, but stark contradictions in the fabric of reality itself. Our understanding of the universe is built on two powerful but incompatible pillars. On one hand, we have Einstein's theory of general relativity, which masterfully describes the force of gravity as the warping of spacetime. It perfectly predicts the orbits of planets, the bending of starlight, and the very existence of black holes. Yet, inside a black hole's heart, general relativity breaks down, predicting a point of infinite density known as a singularity, a place where the laws of physics simply cease to exist. This is where our other great theory must take over: quantum mechanics. Quantum mechanics governs the bizarre, probabilistic world of the very small, of atoms and particles. But the two theories speak different languages and obey different rules. General relativity is smooth and deterministic, while the quantum world is fuzzy and uncertain. Unifying them into a single theory of quantum gravity has been the holy grail of physics for a century, and distant black holes are the ultimate testing ground. Their intense gravity, governed by relativity, interacts with the microscopic quantum particles that flicker in and out of existence at their boundaries. This clash creates one of the most profound puzzles in science, the black hole information paradox. According to quantum mechanics, information about an object, the specific arrangement of its particles, can never be truly destroyed. But according to general relativity, anything that crosses a black hole's event horizon is lost forever, its information erased from our universe. So what happens when you throw a book into a black hole? Does the information within its pages vanish, violating quantum law, or is it somehow preserved? If it is preserved, where does it go? This is not just a philosophical debate. The fate of information determines the fundamental nature of reality, of cause and effect. Studying the simple, pure environment of a distant black hole, free from later cosmic clutter, might finally provide the clues we need. These dark behemoths from the dawn of time are not just destroying matter, they are forcing us to rewrite the rules of the cosmos. The relentless gravity of a black hole warps more than just the path of light, it twists time itself. If you could watch a clock fall toward the event horizon of one of these distant giants, you would witness a truly bizarre spectacle. From your safe vantage point billions of light years away, the hands of that clock would appear to move slower and slower. As it neared the point of no return, the ticking would grind to an almost imperceptible crawl. This is the mind-bending reality of gravitational time dilation, a core prediction of Einstein's general relativity. The stronger the gravity, the more severely time is stretched. Near the event horizon of a supermassive black hole, where gravity is at its most intense, this effect becomes extreme. An hour for the falling clock could equate to thousands of years or even more for you, the distant observer. You would never actually see the clock cross the event horizon. From your perspective, its final approach would stretch out over an eternity, the image becoming ever more redshifted and faint until it simply faded from view. This means that if we could observe matter spiraling into one of the ancient black holes we have been discussing, its final plunge would appear to us as a scene frozen in time, a last moment stretched across billions of years. The universe itself seems to pause at the brink of these dark abysses, offering us a profound lesson in how gravity writes the rules for both space and time, and reminding us that the cosmos is far stranger than our everyday experience can suggest. The galaxies that hosted these early cosmic behemoths were not the majestic spirals or giant ellipticals we often picture. Instead, they were often small, chaotic, and faint, a class we call dwarf galaxies. This discovery appends a long-held assumption in astronomy. For years, we believed that a galaxy's size and a black hole's mass were locked in a strict partnership, that larger galaxies naturally housed larger black holes. Finding billion solar mass monsters thriving in these cosmic backwaters is like discovering a thriving metropolis hidden inside a small, quiet village. It suggests the black hole grew first, achieving its tremendous size long before its host galaxy had a chance to mature around it. The traditional model of co-evolution, where a galaxy and its black hole grow in lockstep, cannot easily explain this. How could a gravitational titan of such immense power exist within a stellar home so comparatively modest? It forces a radical rethinking of that relationship. Perhaps the black hole is not a simple product of its galaxy, but the very engine that built it. The intense radiation and powerful jets from the feeding black hole could have compressed surrounding gas clouds, triggering frantic waves of star formation and ultimately dictating the entire growth trajectory of the dwarf galaxy itself. In these distant, ancient systems, the tail may have been wagging the dog, with the dark heart commanding the growth of its own stellar body from the very beginning. Even the brightest cosmic beacons do not shine forever. The brilliant quasar phase that makes a supermassive black hole visible across the universe is merely a chapter in its life, not the entire story. This dazzling state is fueled by a constant, massive inflow of gas, dust, and stars. But eventually, the black hole consumes all the readily available material within its immediate gravitational reach. The frantic feast slows to a trickle and then stops altogether. The accretion disk, that searingly hot platter of doomed matter, simply fades away. Without this constant source of friction and heat, the intense radiation ceases. The black hole, having outshone its entire galaxy, effectively shuts off. It becomes a quiescent or dormant supermassive black hole. It still possesses the same immense mass and gravity, but it no longer generates the brilliant beacon that announced its presence. This transition from a roaring quasar to a silent giant explains a profound mystery. The early universe was filled with these blazing objects, but our nearby cosmic neighborhood is far quieter. Where did all the quasars go? They did not vanish. They simply went to sleep, their dark hearts still lurking in galactic centers, waiting for a fresh supply of fuel. Finding one of these dormant titans is incredibly difficult. It is like trying to spot a sleeping dragon in a pitch-black cave. You only know it is there if something else, like a stray star venturing too close, briefly disturbs its slumber and creates a faint, temporary flash. This life cycle of activity and dormancy reveals that black holes have rhythms, periods of violent growth and long, deep silences, governed entirely by the cosmic pantry of available matter. That brilliant ultraviolet scream from the first quasars did far more than announce their presence. It fundamentally reworked the cosmos. We are entering the era of the cosmic dawn, a period starting roughly 400 million years after the Big Bang, when the first stars and black holes ignited. Before this, the universe was a vast, featureless fog of neutral hydrogen gas, a lingering remnant from its hot, dense beginning. This was the cosmic dark ages, a time when space was opaque, filled with a haze that scattered light and kept the universe in a kind of dull, gray twilight. Then something extraordinary happened. The first luminous objects, including the powerful quasars driven by those distant black holes, began to flood the universe with an intense, unprecedented form of energy, ultraviolet light. This UV radiation was so powerful it acted like a cosmic blowtorch, striking the atoms of neutral hydrogen that filled all of space and violently stripping away their electrons in a process we call ionization. One by one, the fog began to clear. This was the epoch of reionization, a pivotal transition that lasted for several hundred million years, where the entire intergalactic medium was transformed from a neutral fog into a transparent, ionized plasma, the state it remains in today. Think of it as the universe's great awakening, the moment it turned on the lights and opened the curtains for the very first time. Without this crucial cleansing, the light from all subsequent galaxies and stars would be scattered and blocked, leaving our modern universe dark and invisible to our telescopes. The very fact that we can see so far back in time is a direct consequence of this ancient, violent upheaval, an upheaval powered in part by the furious appetite of the universe's first supermassive black holes. These brilliant quasars are not isolated lighthouses, but signposts charting an invisible architecture. Their positions across the sky are not random, they trace out the contours of the cosmic web. This is the largest structure in existence, a sprawling network of dark matter filaments that stretches across the entire universe, with galaxies and galaxy clusters forming at its densest intersections. Think of it as the universe's skeletal system, an unseen framework upon which all visible matter is draped. But how do we map something made of invisible dark matter? We use the quasars as our survey points, because these supermassive black holes sit at the hearts of galaxies, and those galaxies are themselves embedded within the web. The quasars' locations reveal the web's underlying pattern. By measuring the three-dimensional positions of thousands upon thousands of these distant beacons, astronomers can reconstruct the ghostly architecture they are clinging to. It is like deducing the shape of a giant, leafless tree in a thick fog by carefully plotting the location of every single bird nesting in its branches. Each quasar gives us a single coordinate, but together they outline the vast filamentary branches of the cosmic web, revealing a universe woven together by gravity on the grandest possible scale. This map shows us that the emptiness of space is an illusion, that the cosmos is structured from the very largest filaments down to the very first black holes, all part of one interconnected whole. This cosmic curtain of ionized gas is not the final barrier to our vision. There exists an even more fundamental wall, a point beyond which no traditional telescope can ever see. This ultimate limit is set by the universe's own fiery birth, a time before the first stars or black holes ever ignited. To understand it, we must journey back to a period known as the cosmic dark ages, but not the stellar dark ages we discussed earlier. We must go back further to the very beginning. In the first frenetic moments after the Big Bang, the entire cosmos was an opaque, searingly hot plasma, a dense soup of particles and energy where light could not travel freely. Photons of light were constantly bouncing off free electrons trapped in a chaotic, swirling fog. This lasted for roughly 380,000 years. Then, as the universe expanded and cooled, a pivotal event occurred, the formation of the first stable atoms. Neutral hydrogen atoms captured the free electrons, suddenly clearing the fog. For the first time, light could travel across the cosmos unimpeded. This released flash of light is what we now detect as the cosmic microwave background radiation, the oldest light in the universe. But it also marks a definitive observational horizon. We cannot see any earlier than this with light because before this moment, light was permanently trapped. This means that if any primordial black holes formed in the universe's very first second, any dark seeds born from those initial unimaginable densities, they are forever hidden behind this wall of glowing plasma. Our electromagnetic telescopes, from radio to gamma rays, simply cannot pierce this primordial veil. It is the universe's ultimate censoring of its own earliest secrets, a barrier written into the fabric of space-time itself. The serene image of a planet circling a star is a cosmic line near a supermassive black hole. Gravity here is not a gentle guide, but a violent, twisting force that shreds the very concept of a stable path. Far from the black hole, matter can spiral in relatively stable orbits, much like the planets in our solar system. But as you approach the event horizon, this orderly motion breaks down completely. There exists a critical boundary known as the innermost stable circular orbit. Think of this as the final cosmic racetrack, the very last point where matter can theoretically maintain a circular path before the black hole's gravitational grip becomes absolute. Inside this boundary, the rules of physics as we know them are turned upside down. Orbits become fundamentally unstable. An object crossing this threshold is not just nudged closer, it is sent on a one-way, catastrophic plunge. There is no more circling, no more gradual descent. It is a final, fatal dive directly toward the event horizon. This distinction between stable spiraling and the final plunge is not just a theoretical curiosity, it is the engine behind the incredible power of a quasar. When matter is in a stable orbit within the accretion disk, it has time to heat up through friction, glowing brilliantly with radiation. But when it crosses that innermost boundary and begins its direct plunge, it releases a final, massive dump of its gravitational energy. This process is key to understanding why quasars are so phenomenally efficient at turning mass into energy, far outpacing the nuclear fusion that powers stars. The unstable orbits are not a flaw in the system. They are the final, crucial step in the black hole's feast, the moment the cosmic engine shifts into its highest gear. This hunt for cosmic origins leads us to a profound gap in our understanding, a missing link hidden in the deep past. Between the stellar mass black holes and the supermassive giants lies a ghostly middle ground, the realm of the intermediate mass black hole. These are the objects we desperately need to find, with masses ranging from a few thousand to a few 100,000 times that of our Sun. They are the predicted stepping stones, the crucial adolescent phase that should bridge the gap between the small seeds of the first stars and the billion solar mass titans. If we cannot find them, our entire theory of gradual, hierarchical growth faces a serious crisis. How do you spot such an elusive object from the edge of time? One of the most dramatic methods involves watching for a star's final, violent moments. When an intermediate mass black hole drifts through a dense star cluster, its gravity can snare a passing star. The black hole's tidal forces, the difference in gravity between the side of the star closest to it and the side farthest away, will stretch and pull the star apart in a cataclysmic event known as a tidal disruption. The star is literally shredded into a long, thin stream of gas, much of which then swirls into a temporary, brilliant accretion disk around the black hole. This produces a distinctive flare of light, a specific signature that peaks in ultraviolet and X-ray emissions. For a few brief months, this flash can outshine the entire host cluster, signaling the presence of the hidden intermediate mass black hole. Spotting these rare, distant flashes is like catching the glint of a hidden predator's eye in a dark forest, a fleeting but undeniable confirmation that the missing links are out there, silently building their mass in the cosmic shadows. That brilliant beacon of a quasar is not the only way a black hole announces its presence. For every one we see blazing across the cosmos, there may be many more hidden in plain sight, shrouded within thick cosmic cocoons of dust and gas. These are the cloaked giants, their growth spurt happening behind an impenetrable curtain. When a supermassive black hole feeds, the surrounding material does not always form a clean, hot disk. Often, it is enveloped in a chaotic, dense torus of debris, a swirling storm of cosmic soot that absorbs the black hole's high-energy light and re-radiates it at much longer, invisible wavelengths. To our optical telescopes, these galaxies appear quiet, even dormant, but their silence is a deception. Inside, a furious feast is underway, completely obscured from our view. This is where a new generation of observatories steps in, acting as cosmic translators for this hidden language of light. The Atacama Large Millimeter Array, or ALMA, a vast collection of radio antennas high in the Chilean desert, listens for the faint whisper of sub-millimeter waves. This is the domain of cold dust and gas. ALMA can peer straight through these dusty veils, mapping the furious motions of materials swirling around the hidden black hole, and even detecting the cold fuel reservoirs that feed its growth. Meanwhile, the James Webb Space Telescope uses its powerful infrared vision to see the warm glow of the dust itself, heated by the buried black hole's intense radiation. It is like using a thermal camera to spot a roaring fire inside a bank vault. You cannot see the flames, but you can feel the heat bleeding through the walls. Together, these telescopes are revealing a secret universe of black hole growth, proving that the cosmic dawn was not just an age of brilliant beacons, but also an era of hidden, furious construction, reshaping our senses of how and when these dark giants truly came to power. One theory offers a truly spectacular solution to the growth puzzle. Imagine a star, but not like any star we know today. This is the supermassive star, a hypothetical leviathan of the cosmic dawn that could have contained the mass of 100,000 suns or more within a single, bloated sphere. These would not have been stable, long-lived objects like our sun. Their immense gravity would have created a constant, frantic internal pressure, driving nuclear fusion at a ferocious, unsustainable rate. Their entire lifespan would have been a blink in cosmic terms, perhaps only 1 or 2 million years, for a stellar object that is a spectacularly short and violent life. When such a star finally exhausted its nuclear fuel, its own colossal weight would have had nothing left to support it. The core would have experienced a collapse of unimaginable scale. There would be no gentle fading, no standard supernova explosion to blast its outer layers into space. Instead, the entire star, all 100,000 solar masses of it, would have imploded. The gravitational failure would have been total and silent, with nearly all of its material falling inward, straight through the point of no return. The result would be the instantaneous creation of a black hole seed already weighing tens of thousands of solar masses. This is not a seed you plant and patiently water. This is a fully grown tree appearing in an instant. A seed of this magnitude solves the timing problem beautifully. With such a massive head start, the black hole does not need to feed at its theoretical maximum rate for its entire existence. It has a huge gravitational advantage from day one, allowing it to pull in the dense primordial gas of the infant universe more effectively and begin its growth into a billion solar mass giant within the short time frame the universe allowed. These supermassive stars are the ultimate cosmic shortcut, a theoretical forge that could have created the dark giants we observe at the edge of time. These dark giants are the ultimate cosmic alchemists, forging the very elements that make up our world. While the black hole itself is a gravitational abyss, the violent events it orchestrates are the universe's primary foundries for the heaviest elements. Consider the spectacular collision of two neutron stars, the dense cores left behind after massive stars explode, or the even more dramatic merger between a neutron star and a black hole. These cataclysms, which we can now detect through the ripples in spacetime known as gravitational waves, are far more than just cosmic crashes. In the final moments before the two objects merge, they tear each other apart, ejecting vast clouds of hot, neutron-rich material into space. This ejected matter is a cosmic crucible. Within these expanding clouds, neutrons rapidly attach to atomic nuclei in a frantic process called rapid neutron capture. This is how nature builds elements heavier than iron, elements that cannot be forged in the calm nuclear furnaces of ordinary stars. In these fleeting, chaotic moments, the universe manufactures gold, platinum, uranium, and other precious metals, scattering them across the cosmos like cosmic seeds. Every piece of gold jewelry or platinum ring on Earth contains atoms that were likely born in such a violent merger billions of years ago, a merger possibly triggered by the gravitational influence of a distant, ancient black hole. This means the dark hearts at the edge of time did not just shape the cosmos with their gravity and light, they also filled it with the fundamental building blocks for planets and ultimately for life itself. The fate of a dying star is sealed by a single critical number. This is the Chandrasekhar limit, the ultimate weight limit for a specific kind of cosmic corpse known as a white dwarf. A white dwarf is the dense, Earth-sized core left behind when a sun-like star exhausts its nuclear fuel and gently puffs away its outer layers. It is supported not by fire, but by a quantum mechanical force, a pressure created by electrons packed together so tightly they simply cannot be compressed further. This electron degeneracy pressure is incredibly strong, but it has a strict ceiling. The Chandrasekhar limit is that ceiling, approximately 1.4 times the mass of our Sun. If a white dwarf remains below this limit, it will slowly cool for trillions of years, becoming a dark, crystalline cinder. But if it crosses this threshold, everything changes. This most often happens in binary star systems, where a white dwarf siphons material from its companion. As it greedily pulls in more and more gas, its mass inches closer to that fatal 1.4 solar masses. The moment it exceeds the limit, electron pressure catastrophically fails. Gravity wins instantaneously. In less than a second, the white dwarf's core collapses, triggering a titanic thermonuclear explosion that we see as a Type Ia supernova, a blast so predictable in its brightness it serves as a cosmic measuring tape for the universe. For the most massive stars, however, the story does not end with a supernova alone. If the collapsing core left behind after the explosion is greater than about 2 or 3 solar masses, no known force in the universe can halt its descent. It collapses past the point of a neutron star, crushing itself into an infinitely dense point, birthing a stellar mass black hole. This fundamental limit, first calculated by Subramanian Chandrasekhar, is one of the universe's primary gateways to creating the black hole seeds that would eventually build the cosmic giants at the edge of time. That fundamental warping of space is only half the story, for gravity twists time with equal power. Picture a simple, flat rubber sheet. Placing a bowling ball in its center creates a deep dip, a perfect analogy for how a massive star warps the fabric of space-time. Now imagine that bowling ball collapsing in on itself, becoming infinitely dense while retaining all its weight. The deep dip would transform into an infinitely deep well, a puncture in the sheet itself. This is the essence of a black hole's gravity. The warping becomes so severe that it creates a bottomless pit in the cosmos. The boundary of this pit is the event horizon, the point of no return. It is not a physical surface you could touch, but a one-way membrane in space-time. Inside this boundary, the warping is so absolute that every possible path a particle could take, even the path of a light beam traveling at the universe's ultimate speed limit, curves inexorably inward toward the central singularity. Nothing, not even a single photon, can find a trajectory that leads back out. This is the core definition of a black hole, an object whose gravity is so intense it has carved a permanent prison from which the universe itself cannot escape. For decades, our window to the cosmos was like a porthole smudged by Earth's own atmosphere. Then came the Hubble Space Telescope, a sentinel launched into the clear vacuum of space that forever sharpened our vision. It was Hubble that first delivered the crystal-clear proof of supermassive black holes lurking not just in exotic, far-off galaxies, but in the hearts of nearly every galaxy we could see, including our own. By patiently tracking the frantic orbits of stars at the galactic center, Hubble provided the first direct, irrefutable measurements of these dark giants' masses. This data revealed a stunning cosmic correlation, a hidden harmony between the black hole and its stellar home. The mass of the central black hole was always a precise fraction of the mass of the galaxy's central bulge of stars. It was as if every city in the universe was built around a central monument, with the size of the monument always proportional to the size of the city. This profound connection, discovered by Hubble, suggested that the growth of black holes and the growth of galaxies were deeply intertwined, a cosmic dance that shaped the universe from its earliest days. Furthermore, Hubble's deep field observations peered back across billions of years, capturing the faint light of infant galaxies and the brilliant beacons of young quasars, effectively creating a family photo album of the universe. It mapped the rise and fall of the quasar era, showing us when these monsters were most active, but Hubble also showed us the limits of its own eyes. It saw these distant objects, but often as little more than faint, blurry smudges. It was Hubble that pointed into the darkness and showed us where we needed to look next, paving the way for its successor, the James Webb Space Telescope, to peer into those very smudges and reveal their secrets in stunning infrared detail. Hubble handed off the cosmic baton, its legacy cemented as the telescope that first opened our eyes to the true scale and influence of the dark hearts that rule the cosmos. That popular image of a black hole actively hoovering up the cosmos is a profound misunderstanding. A black hole does not suck. Its gravitational pull at a distance is identical to that of any other object of the same mass. If you were to magically replace our Sun with a black hole of exactly the same mass, Earth and all the other planets would continue orbiting their usual paths in complete darkness. The cosmic demolition does not begin until matter ventures perilously close to the event horizon. It is here, in this final frontier, where the familiar rules of gravity are replaced by something far more extreme. The intense gravity creates a drastic difference in pull between your head and your feet, stretching you into a long, thin strand of atoms in a process called spaghettification. This is not suction, but a tidal force of unimaginable power, a relentless stretching and squeezing that tears everything apart. The true danger of a black hole is not that it pulls harder from afar, but that it offers no second chances once you cross into its unforgiving neighborhood. Its power is not in its reach, but in the point of no return that lies at its boundary. This paradox strikes at the very heart of reality, forcing us to choose between our two most successful theories of physics. On one hand, quantum mechanics insists that information is sacred. Every particle carries a unique identity, a specific history of its spin, its charge, its path through the cosmos. This information can never be truly erased, only scrambled and transformed, like burning a book and claiming its story is lost forever. the ashes and smoke still contain the precise blueprint of the original pages, if only we knew how to read it. Yet, general relativity paints a starkly different picture. It tells us that anything crossing a black hole's event horizon is gone, its information permanently severed from our universe, lost in the infinite density of the singularity. The book is not just burned, it is thrown into a bottomless pit that annihilates even its atomic structure. This is the information paradox in its purest form, a direct contradiction that cannot be brushed aside. So, where does the information go? One of the most mind-bending proposals suggests it is not lost at all, but stored in a holographic form on the black hole's event horizon. Imagine the event horizon as a vast spherical canvas, a cosmic film that encodes every bit of information about the objects that fall inside, not in 3 dimensions but in 2. It is like taking a perfect 3-dimensional sculpture and projecting its entire essence onto a flat screen. The information is preserved, but in a form we can barely comprehend, painted onto the surface of the void itself. Another theory posits that black holes are not eternal, but slowly evaporate over eons through a process known as Hawking radiation. As they evaporate, perhaps they leak this stored information back into the universe, a faint, encoded whisper in the radiation. But if this is true, it forces us to accept that the interior of a black hole and the radiation leaving it are somehow mysteriously connected, a concept that challenges our most basic ideas about locality and cause and effect. Resolving this paradox is not an academic exercise, it is the key to unlocking a deeper theory of quantum gravity, one that can explain the universe from its smallest particles to its largest, darkest giants. The answer, when we find it, will rewrite not just our understanding of black holes, but the very nature of existence itself. The fabric of space-time itself can be whipped into a vortex around these dark giants. While we often picture a black hole as a simple, static pit, many are actually dynamic cosmic whirlpools spinning at velocities that defy comprehension. This rotation is not a trivial detail. It is a fundamental property that dictates how a black hole interacts with the universe. To measure the spin of a supermassive black hole billions of light years away, astronomers perform a feat of cosmic remote sensing, focusing on the X-ray light streaming from its inner accretion disk. As matter spirals inward at near light speed, the iron atoms within it are superheated, emitting a specific, recognizable fingerprint of X-ray light. But when the black hole itself is spinning, it drags the very fabric of space-time around with it, a phenomenon known as frame dragging. This motion pulls the inner edge of the accretion disk closer to the event horizon, subjecting those iron atoms to even more intense gravity. The resulting X-ray signature becomes skewed and broadened, its energy shifted in a way that acts like a cosmic speedometer. By meticulously decoding this distorted signal, scientists can calculate the black hole's rotational velocity. The results are staggering. Some of these ancient behemoths are spinning at over 99% of the maximum speed permitted by Einstein's laws of relativity. A black hole rotating at this limit is not just a gravitational sinkhole, it is an energy factory of unimaginable power. The space around it is not merely warped, it is corkscrewed into a frenzy, creating a reservoir of rotational energy that could, in theory, be tapped. This incredible spin suggests these black holes did not grow from random, chaotic mergers, but from a sustained, coherent diet of gas falling in from a single direction over billions of years, feeding them in a way that kept them spinning faster and faster, like a cosmic top spun by the hand of the infant universe itself. That magnetic funnel guiding matter toward the void is not just shaped by gravity, but by invisible lines of force. Magnetic fields are the unsung architects of the cosmic feast, the crucial mechanism that solves a fundamental problem standing between a black hole and its next meal. The issue is angular momentum, the same property that keeps a spinning ice skater turning and a planet in its stable orbit. gas falling toward a black hole possesses immense angular momentum, which naturally wants to keep it circling at a safe distance forever, like water swirling around a drain but never actually going down. For the gas to fall in, it must shed this momentum, and that is where magnetic fields become the universe's ultimate brake system. These fields, woven through the chaotic accretion disk, act like cosmic friction. They tangle and twist, creating a magnetic turbulence that robs the gas of its spin, transferring that angular momentum outward and allowing the material to spiral ever closer to the event horizon. It is a delicate, invisible dance where magnetic forces orchestrate the final plunge. Without this process, the gas would simply orbit in a stable, cold ring, and the black hole would starve in silence. The brilliant quasars we see from the edge of time, therefore, are not just monuments to gravity, but testaments to the power of these invisible magnetic scaffolds, guiding the flow of matter and energy on a cosmic scale. These powerful jets carve out the cosmos itself, sculpting space on a truly monumental scale. When a supermassive black hole is in its active phase, its influence does not stop at the galactic center. The relativistic jets screaming from its poles act like cosmic blowtorches, but instead of melting metal, they push back against the superheated gas that fills entire galaxy clusters. This intergalactic plasma is unimaginably thin by Earth standards, but it is also incredibly vast and scorching hot. The jets plow into this medium with unimaginable force, inflating colossal cavities on either side of the black hole's host galaxy. These are not bubbles in the sense of soap spheres, but rather immense voids, regions of much lower density that can span hundreds of thousands of light years across. They are some of the largest single structures we can identify in the universe. We can see these ghostly imprints because the hot gas that does remain glows brightly in X-rays, outlining the empty spaces. Meanwhile, the jets themselves light up in radio waves, tracing the paths they took to create these cosmic hollows. Finding one of these bubble pairs is like discovering the fossilized impression of a long-extinct animal in stone. The black hole that created it may have fallen silent millions of years ago, its jets shut off and its feast concluded. Yet the cavities remain, a permanent record of its most violent outbursts. These fossils tell us that black hole activity is not a constant roar, but a series of powerful eruptions. Each bubble pair marks a chapter in the life of the dark heart, an era where it reshaped its entire cosmic neighborhood with blasts of pure energy, leaving its signature etched into the fabric of the galaxy cluster for all time. This profound simplicity is written into the very laws of physics. A black hole, for all its terrifying power, is an object of startling minimalism. According to the intriguing no-hair theorem, a black hole can be completely described by just three simple numbers: its mass, its electric charge, and its spin. That is it. Every single other detail about the matter that fell in, every atomic structure, every chemical composition, every memory of whether it was a star, a planet, or an entire spaceship, is utterly and permanently erased as it crosses the event horizon. All that complex information, all that cosmic hair is shaved away, leaving behind a perfectly smooth, bald gravitational pit defined only by those three fundamental properties. Think of it like this: if you were to blend a grand piano, a library of books, and a mountain of gold dust into a featureless puree, you would lose all the intricate details of those objects. What would remain are just the basic totals, the overall mass, the net electric charge of all the particles, and the total angular momentum from their collective motion. A black hole does this to perfection, becoming the ultimate cosmic smoothie. This means that if you have two black holes with identical mass, charge, and spin, they are completely indistinguishable from one another. It does not matter if one was forged from a single collapsing star and the other from the merger of 1,000 galaxies. They are, from the outside, exactly the same object. This elegant simplicity is what makes these dark giants such powerful theoretical laboratories, reducing the infinite complexity of the universe down to three bare essentials: posing a silent, profound question about what truly matters in the final accounting of reality. This idea reverses our entire cosmic storybook. We have long assumed that galaxies came first, providing the stellar nurseries where supermassive black holes could later grow. But what if the sequence was backwards? A growing body of evidence suggests these dark giants may have been the very first to arrive, acting as primordial anchors around which the first galaxies slowly assembled. This is not a gentle revision, it is a complete overturning of cosmic chronology. The most distant quasars we observe, shining from the universe's first few 100 million years, present an impossible timeline. Their host galaxies are often small and faint, dwarfed by the billion solar mass black holes blazing at their centers. It is as if the foundation stone of a city was laid long before the city itself was even planned, a gravitational seed preceding the stellar structure. How could a black hole grow so massive so quickly unless it was already there from the very beginning, a ready-made gravity well waiting for the universe's first gas to fall into its grasp? Theoretical models now explore this radical possibility, painting a picture of direct collapse black holes forming in the deepest dark ages. These primordial seeds would have created intense gravitational focal points in the smooth, early universe. Vast rivers of dark matter and hydrogen gas would have been irresistibly drawn toward these deep wells, their infill providing the raw material to build the first stars and the first protogalactic clumps. In this scenario, the black hole is not a consequence of galaxy formation, but its very cause, the architect that drew the blueprints for the cosmic structures we see today. The galaxy did not build the black hole built the galaxy. This single, staggering reversal of cause and effect challenges the foundational narrative of cosmic evolution, suggesting that the darkness came first and the light followed. Our cosmic census of these dark giants is about to expand beyond our wildest dreams. The next generation of observatories will not just be bigger eyes, they will be entirely new senses for the cosmos. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will open our ears to the low-frequency hum of the universe. While current ground-based detectors feel the high-pitched chirps of stellar mass black holes merging, LISA will float in space, free from Earth seismic noise, to listen for the deepest bass notes. It will detect the mergers of supermassive black holes from the cosmic dawn, a rumbling chorus from the very first giants as they collided and built the early universe. This will be the sound of creation, a gravitational wave background we have only ever theorized. Then there is the Nancy Grace Roman Space Telescope, a powerhouse designed for cosmic cartography. With a field of view 100 times larger than Hubble's, Roman will conduct vast sky surveys, finding millions of distant quasars and mapping the cosmic web in unprecedented detail. It will find the rarest objects, the outliers, and the freaks that challenge our models, giving us a true statistical picture of how common these ancient behemoths really were. Finally, the Square Kilometre Array, or SCAR, will be the largest radio telescope ever built, spanning 2 continents. Its thousands of antennas will act as a single colossal ear, listening for the faint radio whispers from neutral hydrogen in the early universe. It will map the cosmic dawn itself, tracing how the first black holes and galaxies ionized the primordial fog and lit up the cosmos. Together, these new instruments will transform our silent, static maps of the early universe into a dynamic, multi-sensory movie, revealing not just where the black holes were, but how they moved, how they merged, and how they sang as they shaped everything we see. These dark giants from the cosmic dawn might be rewriting one of our most fundamental assumptions about the universe. The cosmological principle is a cornerstone of modern cosmology, stating that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the cosmos is evenly filled with matter, like a perfectly risen loaf of raisin bread where every slice looks the same. Isotropic means it looks the same in every direction with no central point or preferred axis. This principle allows us to apply the laws of physics uniformly across the cosmos, confident that what we see in our local neighborhood holds true 10 billion light-years away. But what if the earliest supermassive black holes are telling us this is not entirely accurate? Their distribution across the sky is not perfectly smooth. Astronomers are mapping the positions of these ancient quasars and finding hints of colossal structures, vast walls, and immense voids that stretch for billions of light-years. Finding such a structure would be like drawing a map of the world and discovering all the tallest mountain peaks were arranged in a single, straight line, a pattern so immense it defies random chance. If the distribution of these primordial black holes reveals a fundamental lopsidedness or a preferred direction in the universe, it would force a profound revision of our basic cosmic model. The universe might not be a simple, uniform expanse after all, but a place with an underlying architecture far more complex and textured than we ever dreamed, its first structures imprinted by the very first seeds of darkness. Even the event horizon, that final boundary of reality, might be a more violent place than we ever conceived. This leads us to a truly mind-bending puzzle known as the firewall paradox. We have always pictured the event horizon as a smooth, uneventful gateway, a point of no return you could cross without even noticing. For an astronaut falling in, the journey toward the singularity should be calm, a silent glide into the abyss governed by the gentle laws of general relativity. But when we apply the bizarre rules of quantum mechanics, this serene picture shatters. Quantum theory suggests that space is teeming with virtual particles, pairs of particles and antiparticles that constantly flicker in and out of existence. Normally, these pairs annihilate each other almost instantly, but at the event horizon, something strange can happen. One particle of the pair might fall into the black hole while the other escapes, becoming real radiation. This is Hawking radiation, the process that slowly evaporates black holes. The paradox emerges from the fate of the particle that fell in. To preserve a fundamental quantum rule that information cannot be lost, the escaping particle must be intricately linked or entangled with its doomed partner inside the black hole. However, as the black hole evaporates, the math suggests that this delicate entanglement must break in a fiery cataclysm. The only way to resolve the conflict between our two great theories is to postulate that the event horizon is not smooth at all. Instead, it must be a blazing wall of unimaginably high energy particles, a literal firewall that would instantly incinerate anything crossing it. The astronaut would not experience a quiet descent, but a sudden, final impact against a searing curtain of energy. So which is it, a peaceful threshold or a cosmic inferno? The firewall paradox presents us with a stark choice, forcing physicists to confront a brutal possibility that the most fundamental boundary in the universe might be the site of its most violent physics. These ancient black holes are the universe's ultimate archaeological dig. Their light, traveling for over 13 billion years, arrives at our telescopes as an unaltered message from the cosmic dawn, a pristine time capsule sealed by the vacuum of space. When we analyze the specific colors and energies in this ancient light, we are reading a direct report on the physical conditions of the infant cosmos. Every element leaves a unique fingerprint in the spectrum of light, a set of dark or bright lines at specific wavelengths. By studying these spectral lines from a distant quasar, astronomers can determine the exact chemical composition of the gas swirling into the black hole billions of years ago. The results are astonishing. The earliest quasars show an environment almost entirely devoid of heavy elements like carbon, oxygen, and iron. This pristine gas, composed of only hydrogen and helium, tells us we are looking back to a time before generations of stars had lived and died, before supernova had seeded the cosmos with the raw materials for planets and life. This is a universe in its purest, most elemental state. Furthermore, this ancient light can test the very laws of physics themselves. By comparing the behavior of atoms and molecules in these distant quasars to their behavior in laboratories on Earth, scientists can check if the fundamental constants of nature, like the strength of electromagnetism or the mass of a proton, have remained unchanged over cosmic time. A single, faint beam of redshifted light from a black hole at the edge of time thus becomes a laboratory for the most fundamental questions, preserving a snapshot of reality from a moment when everything was just beginning. These colossal structures stretch across the cosmos like titanic searchlights, their beams carving paths through the intergalactic void. The most extreme examples are known as giant radio galaxies, and they are powered by the very same supermassive black holes we find at the edge of time. The relativistic jets erupting from their poles do not simply fade away after a short distance. They can persist, blasting outward for staggering distances, often spanning 5 million light-years or more from end to end. To grasp that scale, our entire Milky Way galaxy is a mere 100,000 light-years wide. These jet structures could swallow 50 of our galaxies lined up in a row. They are not just associated with a galaxy, they dwarf it, becoming the single largest coherent objects we have ever identified in the entire universe. At the very heart of this cosmic spectacle is a specific type of active galaxy called a blazar. A blazar is what we see when one of these powerful jets is pointed almost directly at Earth. It is like staring straight down the barrel of the most powerful particle accelerator in existence. The effect is dramatic, making the blazar appear incredibly bright and violently variable across the entire electromagnetic spectrum, from radio waves to gamma rays. Its light can outshine every star in its host galaxy combined, a fluctuating beacon driven by the chaotic physics of the jet. These are not static sculptures. They are dynamic, living structures, testament to the raw, focused energy a spinning black hole can unleash, shaping the cosmos on a scale that truly defies human comprehension. The universe's most brilliant beacons might be the exception, not the rule. For every quasar blazing across the cosmos, there could be a dozen dark giants feasting in near-total silence. This is the realm of cold accretion, a theoretical mode of growth that defies our standard image of a black hole's dinner. In this scenario, vast clouds of gas do not spiral into a frantic, heated disk. Instead, they fall inward in a smooth, orderly, and almost placid flow. Think of it not as a raging, turbulent waterfall crashing onto rocks, but as a slow, silent river pouring into a bottomless well. Without the violent collisions and friction that create a hot accretion disk, there is no brilliant flash of light, no searing radiation to announce the meal. The black hole gains mass in the dark, a ghost at its own banquet. This cold, direct infall solves a major puzzle. How do supermassive black holes in relatively quiet modern galaxies continue to gain weight when there is no glowing disk to be seen? The answer may be that they are simply eating a different kind of meal, one that leaves no brilliant mess behind. Detecting this process is one of astronomy's greatest challenges. It requires looking for the faintest gravitational signatures, the subtle sway of stars influenced by a growing but invisible mass, or the faint whisper of cool gas disappearing into the darkness. If cold accretion is real, it means we have been missing a fundamental chapter in the life story of these cosmic giants, a hidden phase of growth where the universe's most powerful objects do their work in perfect, silent stealth. This challenge to our three-dimensional reality leads us to one of the most radical ideas in all of physics. The holographic principle suggests that our perception of a rich, three-dimensional universe might be a magnificent illusion. The theory posits that all the information describing everything within a volume of space, every star, every planet, every person, can be completely encoded on its two-dimensional boundary, much like a hologram. In an ordinary hologram, a flat, two-dimensional surface contains all the information needed to project a seemingly three-dimensional image. The universe itself might operate on the same cosmic scale. The information that makes up the world around you, the depth of space, the feeling of solidity, could all be a projection from a vast, complex code written on the distant surface of our cosmic horizon. It is a concept that seems to defy common sense, yet black holes provide the most compelling evidence for its possibility. We have already seen how the no-hair theorem tells us that a black hole erases all information about what falls in, leaving only mass, spin, and charge. But this created the information paradox, a direct conflict with quantum mechanics. The holographic principle offers an elegant, if bewildering, solution. It proposes that when an object falls into a black hole, its information is not lost inside the singularity. Instead, it is perfectly and instantly transcribed onto the black hole's event horizon, the two-dimensional boundary of the object. Every atom, every memory, every shred of data is imprinted onto this spherical surface, stored in unimaginably tiny pixels of space-time. The three-dimensional reality of the falling object is translated into a two-dimensional description on the wall of the prison it entered. From our perspective outside, the information is never truly lost. It is just displayed in a language we are only beginning to learn how to read. This transforms a black hole from a destructive abyss into the ultimate information storage device, a cosmic hard drive with its data written on the shell. If this is true for black holes, could it be true for the entire universe? Are we and everything we see just a holographic projection from the edge of the observable cosmos? The answer to this question may forever change our understanding of what is real. That brilliant beacon does not simply fade into the emptiness. Its energy punches straight through its own galaxy and out into the cosmic void, reaching the most tenuous substance in existence, the intergalactic medium. This is not a true vacuum, but an incredibly thin soup of hydrogen gas, so diffused that on average it holds only a single atom per cubic meter. Yet across billions of light years, this gas adds up, forming a cosmic atmosphere that fills the entire universe. The ultraviolet radiation screaming from a distant quasar travels for eons until it strikes one of these lone atoms. The photon's energy is so intense it violently strips the atom of its electron, re-ionizing it and heating the entire surrounding medium. This process is not a gentle warming. It is a continuous, cosmic-scale heating system that keeps the gas between galaxies far too hot and energetic to ever collapse and form new stars on its own. Without this constant energy input from quasars and other active galaxies, this intergalactic gas might have cooled into vast, cold pools, potentially raining down to form stars in unexpected places and creating a universe that looks utterly different from the one we see today. The quasars act as cosmic regulators, their fierce light maintaining the high-temperature state of intergalactic space, ensuring that galaxies remain distinct islands in a warm sea, rather than merging into a continuous star-filled sheet. This invisible influence, stretching far beyond their own stellar borders, makes these distant black holes the ultimate architects of cosmic structure, governing the very ecology of the universe from their dark, ancient hearts. Our search for the universe's original architects leads us to hunt for ghosts. Primordial black holes are not born from dying stars, but from the violent tremors of the universe's own birth. In the first chaotic fraction of a second after the Big Bang, random quantum fluctuations in density could have caused pockets of space to collapse directly into black holes of almost any size. These would be true relics of creation, forged not from starlight, but from the raw energy of the cosmos itself. The hunt for them is a cosmic detective story, relying on two powerful but indirect methods. The first is microlensing, a subtle effect of gravity on light. If a vast number of these small, ancient black holes drift through our galactic halo, one might occasionally pass directly in front of a distant star. Its gravity would act as a tiny lens, bending and focusing the star's light, causing it to momentarily brighten before fading back to normal. Astronomers meticulously monitor millions of stars, searching for these characteristic, unexplained flashes that betray the presence of an invisible, drifting mass. The second method listens for the echoes of their collisions. When two primordial black holes merge, they create ripples in space-time, gravitational waves that can be detected by observatories like LIGO and Virgo. By analyzing the masses and frequencies of these cosmic chirps, scientists can look for a population of black holes that fall outside the expected range for stellar remnants, a signature of a more ancient primordial origin. Finding them would be a monumental discovery, potentially solving two cosmic mysteries at once. These elusive objects could constitute a significant portion of the universe's missing dark matter, the invisible glue that holds galaxies together. The hunt continues, a patient search for the universe's very first shadows, cast by objects that may have shaped everything from the very beginning. Even the most ravenous appetite in the cosmos must eventually face its limits. Is there a point where a supermassive black hole simply cannot get any larger? Theoretically, yes, and the constraints come from the very processes that fuel its growth. The first is a balancing act between light and gravity known as the Eddington limit. Picture a black hole feasting on gas so ferociously that the intense radiation pouring from its accretion disk begins to push back. This radiation exerts an outward pressure on the incoming gas, and if the black hole eats too quickly, this pressure can become so powerful that it literally blows away its own food supply. It is a cosmic case of biting the hand that feeds you. The Eddington limit defines the maximum rate at which a black hole can accrete matter before its own brilliance stifles its growth. While black holes can briefly exceed this limit in spectacular bursts, they cannot sustain it indefinitely. This creates a natural speed governor on how fast a black hole can grow by accretion alone. The second major constraint emerges when black holes try to grow by merging. When two supermassive black holes in colliding galaxies spiral toward each other, they shed energy by flinging stars away through gravitational slingshots. This brings them incredibly close to within about 1 parsec, but then they hit a wall known as the final parsec problem. At this distance, the region is often cleared of stars, leaving nothing for the black holes to interact with and lose their remaining orbital energy. They can become stuck, orbiting each other for billions of years in a cosmic standoff, unable to get close enough to finally merge and combine their masses. This gravitational traffic jam may prevent many black holes from reaching truly monstrous sizes through collisions. Together, these two natural bottlenecks suggest that while black holes can become almost unimaginably large, the universe has built-in regulations that prevent them from growing without end, preserving a cosmic balance even for its most powerful entities. That final, violent merger is not the end of the story, it is the beginning of a cosmic symphony. When two black holes finally become one, the newly formed object is not a perfect sphere. It is a misshapen, writhing lump of pure gravity, wobbling wildly from the cataclysm of its own birth. This distorted behemoth does not simply settle into silence. It vibrates, ringing like a massive bell that has been struck with unimaginable force. This phase is known as the ring-down, the final act in the gravitational wave performance. Just as a struck bell emits sound waves at specific frequencies that tell you about the bell's size and material, a ringing black hole emits gravitational waves at specific frequencies that reveal its most fundamental properties. The pitch and decay of this gravitational hum are exquisitely sensitive to the black hole's final mass and its ultimate spin. By listening carefully to this cosmic ringtone, scientists can perform the ultimate remote diagnosis. They can measure the mass of an invisible object billions of light years away and calculate how fast it is spinning, all from the faint ripples it creates in space-time. The ring-down is the universe's way of cleaning up after a collision, smoothing out the wrinkles in reality until all that remains is a perfect, silent, and stable dark sphere, its secrets encoded in the fading echoes of gravity itself. The immense gravity of a black hole can transform it into the most powerful telescope in the universe. This is the principle of gravitational lensing in action, where the black hole's mass warps the space around it so profoundly that it bends the path of incoming light. Think of placing a heavy bowling ball on a stretched rubber sheet, then rolling a marble past it. The marble will not travel in a straight line, but will curve along the dip created by the bowling ball. Light behaves in exactly the same way as it passes near a supermassive black hole or its host galaxy. It does not travel in a straight line, but follows the curves of warped spacetime. This bending can have spectacular visual effects. Instead of seeing a single, faint galaxy from the edge of time, astronomers might see multiple, distorted images of it, or find it stretched into a brilliant, luminous arc circling the dark heart of the foreground object. This cosmic magnifying glass does more than just create a pretty picture. It acts as a natural amplifier. The light from the background object is not only bent, it is also concentrated and brightened, sometimes by a factor of dozens or even hundreds. A galaxy that would otherwise be far too faint and small for any telescope to resolve is suddenly brought into sharp, brilliant focus. This allows scientists to study the properties of the first stars and galaxies in exquisite detail, peering into nurseries of cosmic dawn that were once permanently beyond our technological reach. We are not building these telescopes, we are finding them, already positioned perfectly by chance alignments across the cosmos. The universe provides its own observatories, using its most destructive forces to illuminate its own deepest secrets. A single cosmic event can now be witnessed through multiple senses. We are entering the age of multi-messenger astronomy, a revolution that allows us to observe the universe not just with light, but by feeling its ripples and catching its ghostly particles. Think of it like this: for centuries we have been watching a silent movie of the cosmos. Now we have finally turned on the sound and even the subtlest vibrations to experience the full spectacle. This approach combines three distinct cosmic messengers. The first is light, the photons across the electromagnetic spectrum that our telescopes have always collected. The second is gravitational waves, the ripples in spacetime from massive collisions. The third is neutrinos, the elusive, nearly massless particles that fly straight through matter as if it were not even there. Each messenger tells a different part of the story. Light shows us the fiery aftermath, the hot, glowing debris of a cataclysm. Gravitational waves reveal the precise choreography of the merging objects, their masses and spins. Neutrinos give us a direct look into the engine of the explosion itself, carrying information from the deepest, most hidden processes. When we can catch all three from one event, the portrait is breathtakingly complete. Consider a black hole tearing apart a neutron star in a distant galaxy. The gravitational wave observatories feel the initial spacetime shudder, the final, frantic orbits of the dance. Moments later, telescopes might see a brilliant flash of gamma rays and a fading afterglow of light across other wavelengths, the signature of the neutron star's material being shredded and consumed. And if we are incredibly fortunate, neutrino detectors could register a faint pulse, a direct signal from the heart of the matter as it is crushed out of existence. This single, coordinated observation would tell us everything. It would confirm the nature of the objects involved, measure the expansion rate of the universe with new precision, and reveal the extreme physics that forge heavy elements like gold and platinum. This is no longer just astronomy, it is cosmic journalism, reporting on the universe's most violent news with multiple, independent sources. We are finally assembling the full narrative, moving from silent films to a symphony of information, where every note reveals a deeper truth about the dark giants at the edge of time. These distant black holes are far more than isolated monsters in the dark. They are fundamental actors in the grand cosmic story, their influence woven into the very structure of everything we see. They dictated the growth of the first galaxies, their powerful feedback cycles determining whether a galaxy would blaze with new stars or fade into a quiet retirement. They forged the heavy elements that make up our world, scattering the ingredients for planets and life across the cosmos in violent mergers. They cleared the primordial fog of the Dark Ages, their ultraviolet screams ionizing the universe and making it transparent for all the light that would follow. They even test the laws of physics, challenging our understanding of space, time, and information at the most fundamental level. From the largest scales of the cosmic web down to the tiniest quantum flicker at an event horizon, these dark giants from the dawn of time have been silent architects. They are not merely features of the universe, they are essential characters in its ongoing narrative, their gravitational hands having shaped the cosmos from its first breath to the present day. The light from these ancient beacons is a message telling us that to understand our place in the cosmos, we must first listen to the stories whispered by the darkness. 13 billion years of travel, and that faint light carries a story of impossible youth and staggering scale. We have witnessed black holes weighing 1 billion suns when the cosmos was a mere infant, their very existence challenging the speed limits of growth. We have seen how they are not destroyers but creators, forging the elements for worlds and clearing the cosmic fog to let the light of future galaxies shine through. Their gravity bends time, twists space into vortices of energy, and may even hold the key to unifying our deepest theories of reality. These dark giants from the dawn of time are the ultimate cosmic paradox, objects of brutal simplicity that govern the most complex structures in existence. The quest to understand them is far from over. It pushes our telescopes to see farther, our minds to conceive the inconceivable, and our place in a universe sculpted by darkness. This journey to the edge of everything has only just begun. Tell us which of these 50 facts reshaped your view of the cosmos the most.